Hey, hi guys. Good evening.
Hi, good evening.
Good evening, Ankit.
How was your day?
Good.
Oh,
Good so far.
okay, let's just wait for 2 more minutes. Like we will start at 7:05. It's other. It's a join. Hey, hi guys. Very good evening. So let's get started for the day. I want some responding audience. So maybe in the chat you can tell how was your day? Did you do some practice of what we discussed yesterday? If you have got some doubts from our discussion.
Yes, I did some practice. We should
Oh,
talk about,
great.
yeah, using a minist data set from Kaggle and trying to, create a simple model using the
Mm-hmm.
TensorFlow or Keras.
Oh, that's great. Anybody else? Did you face any challenge there?
Yeah, there are some challenges I, face it like, using a activation function with the
Mm-hmm.
sigmod or using a epoch, that how much
Mm-hmm.
epoch we have to use. And because
Mm-hmm.
sometimes I have changed the values of my loss of function, but not getting
The optimum results.
yeah, optimum result. Like, if I change it something, then it's giving me 85, but changing it, it will give me 84 or 86. Not changing drastic change into that. So
Uh,
that kind
yeah,
of a
that
thing that I
that
think.
happens. Yeah. That is again something called that hyperparameter tuning that we do in conventional machine learning models. Similarly, we need to get to some parameters for which our model is performing optimum. Also, one question for you all guys. What do you think is the when you say optimum performance, what is the level of accuracy you can expect from the model before categorizing it to a optimum? Or what is the acceptable range of your model accuracy?
See,
And for yeah,
if I get 85, between 85 to 90 is very high, but if between 85 to 90, if I'm getting accuracy from my model, that I feel that would be good achievement by model
hmm,
itself.
okay. Anybody else? Samshi says 85 to 90.
So for medical data set, I think it has to be around more than 95%,
Okay.
because we cannot, the false negative we cannot accept in medical
Mm-hmm.
context. So around 98%, 98 to 99% is
Mm-hmm.
fairly a decent accuracy, I would say, in medical context.
Okay. Shashwat says 98 to 99%. And that is 90%, 80%. That is also correct. 98, 99%
Yeah,
is
it
also correct depending
depends
on the use case.
depending on the use case. Yes,
Yeah.
yes.
Okay. Do we have, why are everyone so silent today? Maybe you can unmute or you can type it in the chat, whatever you think. What is the optimum accuracy?
I think it should be more than 90% in most of
More
the
than that.
cases.
Okay. Okay. So by now we have three groups of accuracy right now what we are discussing. 85 to 90 is something that can be acceptable. Shashwat says it should be 98 to 99% depending upon the use case. And Kalpana says it should be more than 90%. But what if I say even if a model is performing at 50% or 60%, there are chances or there can be that 50 and 60% is also acceptable. It completely depends on the data. It
Yeah,
completely depends on the
this we
use
can take
case.
it as an indicative direction, just
Yeah,
to get we cannot do any specific activity, but we'll get an indicative direction that okay, this is going this way. Yeah.
yeah, exactly. It completely depends on the data that you are feeding into your model. If the data actually captures all the essence, if it is missing out some of the essence which can help in predictions, right? Sometime it can happen that you are getting very good accuracy on your training data, but whenever you hit the real or unknown data, your accuracy can go down. That's what we called overfitting. That's we discussed yesterday, right? Uh, okay, so for this discussion, we said we can conclude it by saying that there is no fixed number we can put. Different use cases, there can be different acceptable range. Just like Saswat mentioned that for medical use cases, we cannot afford to have false positives, right? That is use case to use case basis. Then, but again, it completely depends on the data that you are feeding in to the model. The accuracy can be improved by data cleaning, maybe hyperparameter tuning, using better models altogether. There are different scenarios in which through which you can improve your model accuracy, but it completely depends on the data. Right? This is what we have discussed yesterday. If you have any doubts from our yesterday's discussion, do let me know. We can take 5 minutes and then we can start today's agenda. Yeah. We discussed about different type of machine learning models, brief overview on the neural network, some internal architecture of the neural network, some of the key terminologies that are there in my neural network, what is the learning mechanism of my neural network, feed forward, back propagation, forward propagation, recurrent neural network. We also discussed some of the use cases around this, right? And we have discussed around the framework of TensorFlow and Keras, which helps us building those neural networks. It makes us our life easier, right? This is where we concluded yesterday. If you have any questions, let me know. Else we can move forward. right? So for today's agenda, the topic called transfer learning was listed in my agenda from yesterday's session, but since we could not complete it yesterday, we'll take it up as the first topic today. Then we'll be moving towards the transformers, because from moving from our neural network model to transformer, this is the transfer learning that makes it possible. That attention mechanism that is available in my transformers is what makes it different from all the other neural networks, right? Once we are done with the transformer architecture, a brief overview on the internal working of our transformers, then we'll be moving towards the AI, because transformer is the step between our neural network and the large language model. So transformers becomes an important topic there. Once we have idea of that, we'll be discussing what is my artificial intelligence and what is my generative artificial intelligence, and moving towards LLM, what is large language model, why it is called language model, first of all, different types of large language model out there in the market, which we can use, how they are categorized, some of the key terminology, just like we discussed some key terminologies around neural networks, we'll be discussing the key terminologies in our large language model. When we are using the large language models, these terminologies should be handy for you to grasp thing, to understand the model faster, which model to go for, which model not to go for. These concept will help you understand that part as well. And then we'll be looking around some of the key concept, like the prompts, how you write a prompt, some of the parser, what does the parser mean, how to do that. We'll also see some hands-on over there, right? Everybody clear on today's agenda? I can proceed further then. Maybe type yes in the chat or unmute yourself
Yes.
so that we. Okay, great. Thanks, Kalpana. Thanks, Ashwath. Thanks, Shravan. So moving forward, starting with first agenda of the day, that is called transfer learning. What is transfer learning? As the name itself suggests, we are going to transfer the learning from one model to another model, right? So that you have trained your model on certain knowledge bank that you had, and whatever the understanding that you have gained in the training process, you are transferring that learning, and it is different from machine learning. If you say that in our machine learning model, we are training the model on a set. Let's say it was trained on the feature A, B, and C, and D, right? There are 4 features on which it is trained, and there are different values of these 4 parameters, and you are supposed to predict a variable called Y based on these 4 input parameters. In conventional machine learning model, the values of this A, B, C, and D can change to predict the target variable, which was X in this scenario. But in transfer learning, we can expose to a completely new feature that can be, let's say, E. And the learning that the model has got from A, B, C, and D can be used to predict something that is completely new that the model has not even seen, just by adding some manipulation to the model. That's what we call as transfer learning, right? For example, like maybe this example can help you understand it better. That let's say you have trained a model which classifies whether the input images are of a dog or not. It will just classify whether the image can be the image can be of different kind of dogs. It can be puppies. It can be different breeds of dogs altogether. So your model has learned some features that depict or that identify a dog in the picture, right? So your model already understand how to extract those feature, how to understand whether a particular pattern it belongs to a dog or not, right? So here you have made some learning already. But when it comes to transfer learning, you just do some like minor tuning in to your model. Your model already know how to recognize those patterns. It's just that you are changing what pattern to recognize. You are doing some additional tuning into your model, and your model should be able to understand a picture of a cat as well, because you are transferring the learning that it had gained to extract the feature, to understand the feature, to understand the patterns. You are just changing the pattern, what pattern to look for. That is called a transfer learning, right? Simple example in this scenario can be voice detection. like our Alexa. It understands, it recognizes the sound, it respond to the sound around by, but it also responds to the wake up word. Once the wake up word is recognized, then only the next thing happens. Otherwise, it is silent all the time, correct? So it is just as you are training a model on certain features, and then you are just doing additional minor fine tuning so that you can leverage the pre-training of the model into some new task. It is very helpful when you have a very limited, or say, let's say very limited data of some of the feature which you want to leverage. So you can have some training of your model on the abundant data, which is similar to your final data point on which you want the response around, and you can leverage that part. Example around here can be movement detection to face detection. So let's say if you have a visual, like a convolution or neural network which is detecting all the feature in a video frame, right? And there you want to detect a face, particularly face recognition systems, right? There you already are recognizing the pattern, and you are just additionally fine tuning your model for face detection. So in this particular scenario, there is something called pre-training. Plus, let's say you are doing some fine tuning. This is for the additional feature that you have. Right? And then you can use the pre-training learning and with some additional feature to gain a completely new model to work on new feature, right? This is a very important aspect when we are moving towards our large language model, because there is something called inferencing stage, there is something called pre-training stage. So this pre-training stage is nothing but this stage where we are training, we are showing abundant of information to our model so that our model uh, predict, or model learns how to predict the next thing. One example, if I can give, is uh, this pre-training is equals to, let's say you are walking, you are learning how to walk, right? Once you learn how to walk, you can apply this same thing in different scenarios. Different scenario can be you are running, right? Let's say you are a sprint. Sprint can be part of this only, but let's say you are riding a bicycle. You are learning how to balance. Earlier, you were learning how to balance on your feet, then you are learning how to balance on two wheels. Once you have the learning of your riding a bicycle, balancing on two wheels, easily you can move towards riding a motorbike, right? So you are transferring the learning from one stage to another so that you can grab up the things quickly, right? This is what the whole concept around transfer learning is, that it is very important for all our generative AI models that are out there in the market. Just let me know if you guys are able to grab the transfer learning concept. This is an important concept which you should be aware of. If you have any questions, please put it in the chat. Okay, thanks, Ashwa. Thanks, Kalpana. If nobody has the doubt, we can proceed further to understand the next concept or the next agenda for today, which is my architecture for the transformers. What is transformer? We can move towards that. Okay, so, great. So we'll be moving towards transformers now. Transformers is evolution of my neural network. It is a neural network internally, but it is much more complex, much more evolved in terms of application, and it can process a large amount of information. It can have something called essence of your statement. Let's say you are writing, um, my day was good. Let's say you are writing a statement, my day was good, right? And then you are saying my day was pretty good. The statement more or less meaning is same, but the meaning of pretty here is not equal to, let's say when you say my dog is very pretty, or let's say my girlfriend or my boyfriend is pretty. So in that scenario, right? So the meaning of this term pretty can vary in different scenarios. So these transformers helps you depict that meaning, understand that meaning, the different scenarios the word can hold, and it can help you process that information. So from our conventional machine learning model, the neural network internally is transformer internally is a neural network in itself that process entire sequence at once, just like we had in our RNN, where the whole information is feeded into my neural network at once. It is aware of all the other information that is available adjacent to your input that you are sending, and it can process that large amount of information. What makes it different from my conventional or my other neural network is that it has something called positional encoding. What is positional encoding? Let's say you have a statement called I love dogs, right? So here the position of one is I is 1, the dog is at position 2, the position of the love is 2, and dog is 3, right? So this is my position. Each the occurrence of a word, at what position it is, and what is the relation of dog with love, right? How they are correlated, right? Now let's say if you add something in between called I do not love dog, right? So the sentence meaning itself completely changes, right? So this positional encoding helps model to understand the relative relation between different words that are occurring in your sentences, right? So your this is a broader overview or the architecture of my transformer model. Internally, we'll be discussing some of the aspect of it as well. But let's say you are giving something in the input and which is converted into embedding. Embedding is nothing but your numerical representation of the input text, or the input, not only text, whatever your input is, it is the numerical representation of your input, right? We'll be discussing that in detail. Input converted to embedding. The embeddings can be of sparse and dense. We'll be discussing what that sparse and dense is. But what is the main feature of my transformer? What makes it different from the previous one? One, I mentioned that it is positional encoding, and the other one is called attention mechanism, right? Attention mechanism is it can correlate those terminologies, but it can correlate between 2 and 3. It can correlate between different aspects. Sometimes the word may or may not have adjective. Sometimes what is the relation between my verb and my noun in a given sentence, right? So it can find that correlation. It can have that attention mechanism within itself, which is what was lacking in my neural networks, and that's why the transformer has completely evolved or completely changed how we used to use our neural network. This architecture started from translation, right? So if I translate one sentence from one language to another language, the meaning can completely change, right? Let's say you write a sentence, I eat pasta. In Hindi, if you translate the exactly same sentence, the meaning can be I, that means me, khaya pasta. But we do not translate it like this in your Hindi language, right? In Hindi, you can have this statement, this particular word at last, but pasta can be at the early, like prior to the verb, right? So this architecture, how this can be controlled or this can be managed, is what the architecture of positional encoding and attention mechanism helps us control this information, right? Any doubt till here? This is a broader overview. We'll be discussing a bit of this in detail, but this is a broader of what a transformer do. This transformer is further evolved into large language models. So this is an important part in here. We won't be going in too much of details, but we'll be having a brief idea of what transformer do. Any doubts, please put it in the chat, or we can proceed further.
So transfer is itself a neural network, right?
Yes.
So why it overcome the shortcoming of neural network if it is itself a neural network?
Okay. So let's say there is a a motor engine that is within your car, right? That is also engine. And then you have an engine in your plane, right? Are the two engines same? Maybe no, right?
No. Yes,
But
no.
both are engines. Both are doing more or less the same thing. There is a piston that is moving, there is a fuel that is burning, right? And there is some energy that is generated, which is then converted to move a wheel. In terms of a car, that energy is used to rotate your wheels, which is touching on the ground. You have a friction from the ground. But in a plane, there is a turbine that is moving, right? So the engine is there. The key concept inside that engine is more or less similar, but they are completely different. Similarly, in this case, internally, it is a neural network, but how it is built, how the architecture is configured, what is the application, what is the use case, right? It is completely different. Got it?
Yes, got it.
Yeah. Any more doubts?
Can you please explain about positional encoding one more time?
Yeah. So positional encoding is like when I am translating, let's say this particular sentence called I eat pasta, right? When you are translating it, you are not just translating it one by one word for any sentence, for any language when you are translating. The translation needs to be word by word, right? It can be that sometimes this eat can be later on in a different language. Like in Hindi, the meaning of this word eat is coming at the end, whereas the pasta, the actual thing that you are eating, that can come a little prior to that, right? So the meaning has to be the same, but the position of this word can definitely change the meaning. So this positional encoding helps you or helps the model understand what is the meaning of that particular term with respect to that particular sentence, and when it is translated, that essence has to be there. The correlations has to be there when you are moving it to the different language. If the correlation is not there, that means something is missing, something is off. If I translate it word by word, it definitely is not a correct statement.
So what positional encoding do? Like
Uh,
it'll
Positional encoding helps the model to understand the correlation of the term coming at a different position within your statement, within your input, whatever the input that you are providing. That position can definitely impact the whole scenario altogether. So this positional encoding helps you do that. So this is encoded as 1, 2, 3, 4, 5, whatever the number of tokens you have. We will be discussing tokens a little later.
okay.
But for each token, you have some positional encoding attached as soon as your input is added into your transformer. Okay. Shall we proceed? Or do we have any more doubts? We can discuss this one a bit in detail as well. Okay. So attention is all you need, isn't it? Everybody needs attention in some form or the another, right? Even the transformer needs attention. Attention mechanism has changed the game altogether. This is the key difference that helps transformer learn whatever the pattern that it is trying to recognize and whatever the task that it has been provided. That allows to model focus on different parts from the input sequence. So input part can be, sometimes it can be a verb, sometimes it can be a noun, sometimes it can be an adjective, right? The longer statements, there can be correlation across different part of the statement. How much, let's say, in my previous statement, let's say that was, I love pasta, right? What is the impact of I on pasta? What is the impact of love on pasta? How this attention can be distributed across different element in my statement, different tokens that are available in my statement. That is what my attention mechanism helps me do. And this was the name of the research paper that was published a couple of years back, around 2015, 16. And this image that I have taken is directly from that research paper itself, which defines the internal architecture. This was the block that we had seen in the previous one. This is the internal, how it goes within a neural network, right? So you, as soon as your input encodings are fed into your neural network, this is my input text. It can be input image, it can be input voice, it can be whatever the information that you want your model to perform, take action on. It can be input that you pass in, and then you feed in the positional encoding to the model. So it is like you are adding a statement, and with the statement, the model adds some positional encoding on this particular input that you are adding into your model. And then there is something called multi-headed attention. So let's say how a particular text is converted to into an embedding. Let's discuss a bit on that. That will help you understand what is multi-headed attention. Okay. So let's say you have a long list of vocab. Let's say you have 50,000 words in your vocabulary, right? So all these 50,000 words, let's say, are there in your, let's say there is a table which has all the 50,000 words available in your vocabulary, right? And let's say it include all the words that are there in your vocabulary, and whatever the words that come in the input, it matches with wherever this particular word exists, and it brings up whatever the embeddings were there for that particular term itself, for particular single token itself. And that's it. That's called that. These are the static token, static embedding. Right. So this is a embedding of a particular term that is already available with you. This is been available all the time. Not all the time. So it was generated earlier, and you can leverage this. So, but this is the single embedding of a single token. You cannot use it directly because it is part of a statement, right? So you extract the embedding of all the statement, and you add them up together so that you end up with something like a metric which has some embedding tokens available, which you can consume, or which you can say that this embedding depict my statement, whatever the statement that you have provided, right? Maybe if you watch some of the YouTube video which has a really good animation of how this whole thing is converted, that will be good. I can suggest some of good YouTube channels which you can browse through. But just imagine that you have, let's say, a bag of a code for each word in your vocabulary, and you just pull that code, whatever the sentence or whatever the word that is available in your vocabulary. You just pull that particular encoded value, and you just club all the values together to get an embedding for your statement. I can put it simply in that manner, but I would definitely suggest you to just go through some of the videos so that you can understand how actually embedding internally work. For multi-headed attention, there are some layers that are added, and these are some layers which the some questions which the model has to answer so that it can actually understand the meaning of that particular statement. Once it can be like, let's say, 32 layers for the BERT model that are there. It can be vary depending upon how you want to configure your network. But for BERT model, it is around 32. And once you have this, so over here, there happens a lot of calculation, a matrix multiplication, because your statement has to answer a couple of questions, and each answer itself is a embedding. There is nothing that the model understands which is text. It only understands the numbers. The numbers or embedding is the numerical representation of your input statement, or any text data or video data, whatever your data is. Embedding said that is that numerical representation, and your model has to get all those understanding of that input that you have given from that defined layers of attention that you want to focus on. And then it is normalized. Normalized as in, because the output sometimes, or let's say many times, is not defined. Sometimes it can be 1.0 plus 1.0 minus 1.5, and let's say then there is plus 13. Let's say then there is plus 4.5. Let's say then there is minus 3.4, right? So this is not scale. This can exponentially increase the complexity of your model, right? So this complete embedding has to be normalized so that it capture the essence without losing out on the information. You can just reduce the magnitude of these and scale them up. That's where we are doing normalization and all. And you pass this information further to a neural network, which is again a feed forward neural network which processes the information. There is a feedback loop inside also, which works around it. And then again, this particular block, do you see this NX? NX is like how many time you want to iterate over this loop. The more you iterate over loop, the more you understand the bit data. But if you iterate too much, you might face the problem of overfitting. If you do not iterate much, you might face the problem of underfitting. This is something called epoch, which we mentioned a little time ago. Epoch is how many times you want your model to iterate over the data and capture the data and essence of the data, understand the data, right? That is called epoch. Similarly, on the output side, your output starts from here. Your output from this left side of the block goes inside here, and here you have again some complex architecture that are happening, right? If you see, this part again is same, but there is something called masked multi-headed attention, which are some additional layer that are available to capture the essence of that particular statement. This whole and there is something called softmax. Softmax is the activation function that is used in this particular scenario. Remember, we discussed about the activation function yesterday, whether this particular neuron, for at a neuron level, whether it has to fire or not, right? Similarly, for this particular neural network also, this is the output layer, and at the output, you have something called activation function, whether the output of this particular scenario can be a true or a false, or what it can be, right? Uh, uh, are you guys able to understand what I'm trying to say? Sometimes it can be overwhelming, but um, trust me, I'm trying the easiest possible way to help you guys understand how things are flying.
Can you explain this positional encoding and the this one multi-head attention?
Yeah. So in positional encoding, your input statement, let's say this was your input statement, which had 10 words, right?
Yeah,
It can be any, let's say it was a text statement that you have added,
yeah.
and each word has some position in your statement, right? The position sometime itself also has the meaning,
Okay,
right? So that position has to be preserved to capture that essence of the meaning. So this positional encoding helps in that only, that what meanings that word hold. If you add the position of that word as well, it can help you understand the meaning of that. That's what is happening, or that's what positional encoding is helping in, right?
okay. So positional encoding will be you see this is once you embedded the this one. Okay, the input
Mm-hmm.
is embedded. So how
Mm-hmm.
you add that position value to that, or how it will be incorporated in the feed forward mechanism means.
No, so when you give the input, you have the embeddings available for each token, right?
Yes, yes.
Right?
Each token is available. Yeah.
Yes. And you add that positional embedding. What is the positional encoding of my first token that is coming input? Then we
So
have
it
the
will be
second token coming in.
say 0001. It is added to
Hmm.
that right.
Yes, yes. So that it captures not only the essence, but it also, when the model is trying to understand the information, or let's say when
Or
you are
it's
trying to
like that.
understand.
It's if it is
Hmm.
added, it become another word, right? See,
No.
embedding. For example,
Hmm.
embedding. We say that A is 001, B is 002. Like that, something we will be encoding. So when you
Mm-hmm.
add something 001 to 001, which is A,
Mm-hmm.
it will become B, right? So position
No.
will be
So
a separate. Either it should be a separate digit or something like that. It should be there.
no,
I'm
no.
not getting
So
that.
if I give you an example,
Mm,
so there is something called when you encode a text, the
mm.
meaning of the word can be changed in a different scenario, but when you decode it, you are able to get the exact message that was encoded, right?
Yes, yes, yes,
Yes.
yes.
Sometimes if you talk about some digital signal or some analog signals, you are modulating your signals in some scenario, right? But when you reduce it to, you want to reduce it to your original form, you can extract whatever the original information was there. Correct? So this is what
Yeah.
my positional encoding is doing in this particular scenario.
No, embedding is that encoding and decoding happening for embedding, right? So if I say, for example, if you can give one example, that will be better to understand. So for example, if we say word talk, so we encode it maybe based on something. For example, there are 1,000 words in my sentence, so I will maybe 1,000 numbers with digital numbers we will use, and each number will be given based on that it will be given some binary values, assume.
Okay.
So this binary value comes to positional encoding. What will be added to that? That's my question actually.
Okay. So let's take a scenario if you talk about in terms of binary.
Hmm.
Ideally, it is not binary, but let's say it is a binary thing. If I add very minute uh, magnitude, let's say I shouldn't take it binary because it is never binary. Let's say it was minus 1.1, it was 1.2, it was 0.3, it was plus 0.3, it was minus 0.4, right? And let's say for a positional encoding thing, I just add something very which is very minute and that impacts only certain elements in my vector. I'm not changing the complete vector. I'm changing something, some of the weights, which are very minute. This is just for holding the position, not to change the meaning. And when I'm depicting, when I'm finally interpreting, I'll know that what all weights I have added, or not weights, but what all position I have changed in my current vector.
This
And I can just,
1.1 you are saying will represent a word.
no. It is so okay. So an embedding can be of length in 1024. The OpenAI embedding that are there, that is of length 1536. And when I say 1536, it's an array of these many elements. It's a list of these many elements that are there. It
Okay,
is
one
not.
five.
It is
It
never
will have
one
one five
word.
three. It will have
Mhm.
1536 uh,
Yes.
uh,
Tensors.
tensors. Okay.
Yes, it will hold that information, and it is 153. Sometimes there can be model which are even bigger than this, with the vector is even bigger than this. Sometimes it can be even lesser
So
than
the
this.
1536 digits will be there, right?
Yes, 1536 elements will be there in this
One word
vector.
will be represented with the 1536 digits.
No, yes, correct. One word is represented with one of this, and when you
So
have
that
this
may,
one word, one word, one word, you add all of them.
so
Then
this
when
1.1 is the one digit number, right?
yes,
This 1.1 will be, see, anyway finally it will be the machine will know only zeros and one, right? Ultimately.
no. It is in points as well. It can be negative, it can be positive. It is not just 0 or 1. It is not binary.
It's, okay.
Was it you were confused with?
No, no, I am saying that. So, for example, talk is a word that will
Hmm.
be represented as 1.1. You are saying, correct?
No, no.
What
Talk
is
is a word which can be represented in 1536.
1536?
Yes.
Yeah. So, what is this 1.1 example you are shown in the top?
Yeah, so this is one single array. This is one single word. Completely, this is one single word. 1.1 itself does not hold a meaning. But when I see this whole pattern or see this whole array together, then it holds the meaning of a particular word.
Okay. So,
Yeah.
see, ultimately it is 1536 digits will be there in the word, correct? Is it that binary or whatever is the number?
Mm-hmm.
That means characters will be there, correct? That's
Mm-hmm.
what it is meaning, correct? So
Yeah.
this word talk will have converted to that much numbers, correct?
Yeah. Correct.
That much numbers. So when I
Mm-hmm.
am adding a positional encoder to that,
Mm-hmm.
so it will be incremented by something, correct?
Yes.
So when it is incremented, this 1556, that much, that will represent another word, right? It can move to another word.
No, it is not like that because internally my model also know that there is positional encoding added. It also knows how the relation, how to correlate those words internally. It is not that you are just having let's say you have a positional encoding that is 1536 and you are summing up both of them. Your model understand what is the positional encoding attached to this vector. It is not that, let's say,
So that
your
means
position was
that
0.1,
means if
0.3.
the word length will become 1536 into 2.
No,
If it is
no.
added to this, my question is that the
Mhm.
1536, see, it will be a continuous series of words, correct? For
Yeah.
example, if one sentence will have 1536 maximum words can be there, correct?
Okay. Okay.
1536 words can be there. So each
Mm-hmm.
position there will be one word from that chunk, correct?
Yes.
So that chunk one word will be there, and this 1536 will have a continuously that much number will be there,
Mm-hmm.
correct? So
Yes.
when I am adding one more number to this, that
Okay.
one
I
number will
think,
become another number continuous if you
yeah,
take it
I
as a
think I
continuous.
understood. I think I
Yeah.
understood what you are saying. So let's say, just correct me if I'm wrong. And
Huh.
so let's say there is this one word which is of 1536 length, and there is something called 1.1, 1.2, minus 1.5, minus 3.6, plus 0.4. There is some continuous lists like that is
Yeah,
for
you represent that
1536 length.
continuous
Correct. And
numbers.
then
Yeah,
you
yeah.
have encoding for your position, which is, let's say, 1.3,
Yes,
0.5,
yes, yes.
0.2. And then you are saying you are doing a matrix, not a matrix, but
Addition,
mathematical addition. No,
addition.
it doesn't happen a mathematical addition.
Okay, what
This
addition is?
this this particular position is attached to this vector. Attached, when I say, I'm not saying adding. I'm not saying
Okay,
that this
it
will
will
be
parallelly go.
concatenated.
It will parallelly go
It
to the.
will parallelly go. Yes,
That
it will
was
be
my
attached.
question. Correct. Now I understood.
So
Now
is it
there will
kind
be,
of mapping, Ankit?
Yes, sort of. Yes,
it will be two set of information will go to that. Correct.
correct,
That much
correct.
new neurons will be added. For example, if it
Yes.
is positional encoding is be added with some 5 digits, the another five
Mhm.
digit set will go parallelly to that.
Yes. Another
Yes.
5 digit, that is something you will add as a metadata information.
Yes,
We'll
yes,
come to
I
that
understood
later,
now. Now,
but that
now
will
it's
be
clear because now
attached.
it can clearly understand that. Okay. Otherwise, if
Mhm.
it is mathematically added, it become another word. Correct.
It can have an
Ah,
impact on my
yeah,
word.
yeah,
Yes.
yeah.
Yes.
See this
So,
position, this input embedding, do we
mm,
convert into a vector format
yes.
somewhere?
Yes.
Positional values
Yes.
will
It
be
will
there,
be.
right?
Yes. It will be
It is
there. And
not
so
direct
whenever,
embedding, na? There will
yes,
be a
it is.
positional. This thing will be there, correct? No.
Correct. So whenever you are trying to make a sense of a particular word, when I say word, that means you are trying to make a sense of a particular vector, embeddings
No. So
array, right?
it will be embedding vector, correct?
Yes, yes.
Okay, okay, understood.
Whenever you are trying to understand the meaning of a particular vector, you also take a look at the position of that particular vector in the statement.
Yes, yes.
It is
Now,
not independent. The
now it's
position
clear.
does make
Now
a
it's
difference.
clear. Only can
Yeah.
you explain this multi-headed attention?
Yeah.
Uh,
So multi-headed attention, not multi-graded
yeah.
attention. Yeah. Let me clear this. Yeah. So in multi-headed attention, let's say there are certain list of questions that are available, which your statement has to answer. Let's say first statement was, let's say, is it about any animal? Let's say your statement was, I love pasta only. Okay. So your answer can be, let's say, is it about animal? Again, it can be a yes or a no. Let's say it was a no. Is it about Indian cuisine? You can say a no. Is it about something to eat? About, first of all, it can be yes. It is something related to it. So these are like uh, to capture different essence of your word, right? Of your statement, not a word of your statement. The essence, what it actually means. These are some of the input that are like your process through your input, so that you can understand, or the model can understand the meaning of this. And these internal questions, or these internals are all configured inside the neural network. These are not on GPT models already. All of them has this kind of scenario, but these are not um, made out, right? So it passes through each and every layer. So each individual question is one layer. It is multiplied with your additional based on whatever the answer is, yes, no, whatever the response comes in. Your current, whatever the input is going, it process through it and is updated based on the whatever the output is. And then model tries to understand, okay, it was referring to something that is related to it. It is something that was some that the
So there will be a matrix, pre-configured matrix based on the
yes,
type or something.
yes,
It's like it's related to food, it is related to country, it is related to
yes,
technology, it is related to ABC mathematics, it is related
correct.
to chemistry. Like that, there will be some matrix will be created. If that is related to that, it
Mhm.
will be marked as yes.
Correct.
But who will identify that based on the what it will be
So
identified that it is belong.
once you build your this transformer architecture, once you are configuring, everything has to go in the input.
So input. So before that, where it will be processed that okay, this is while doing the vector, it will
Hmm.
be saying that it is more related to maybe some based on the relation. It will create some value to that.
Hmm.
How it will be the multi-headed attention. So you are
Uh-huh.
saying that we should give this input also to the
Mm,
it
no, so
will
when
go as
you
an input.
are no, so when you are building this transformer model, then yes. If you are consuming it, then no, because it is already configured, everything is in place, and you are just consuming
No,
it in the
no,
shape and
no.
form it is
In the
available.
first case, I am asking
Mm.
when you are building the
Yes,
transformer,
you configure all the scenarios internally. Yes.
the input, for
One.
example, from my sentence, I love
Mm.
pasta. Sorry. Okay,
Hmm.
so then input embedding, there will be a positional encoding will be there. There will
Yeah.
be a vector related to this will be going, correct.
Hmm.
Each word will
Yes.
be going,
Hmm.
and where this multi-headed attention information will be processed and added,
Yeah.
where it
It
will
will
be
be headed
processed. The process
inside.
first, it need to be processed, right?
Yes.
So where it will be processed? How
It
it will
will
be
be
processed?
processed inside your transformer. Just like inside a neural network, there are calculations going on. Here also, there are some matrix multiplication that will go on for each and every process that we are doing. It
So
will be
how do
happening.
you know that okay, I love this pasta? So
Hmm.
how I know that it is related to food?
That's what you configure inside your model.
It is based on the vector. For example, food and this word is very closer in
Hmm.
vector. Then
Hmm.
I say that okay, this is related to food. Like that, it will pick up.
So there are some pre-configured answer. Let's say whatever input comes in, you are not at all aware of whatever the input comes in. Based on whatever the standard question that you want to ask, you try to go as close to possible to your whatever the input has come in. And
Mm.
that's where this question, multi-headed question that comes in, that you are trying to understand the input that has come up.
Mm.
And once you, let's say, you are asking multiple questions, you are getting closer to your the input statement. Once you say that, okay, I am close enough to the input statement, then you say, okay, now let whatever input come in, I'll be able to understand what this scenario is. Let's say in terms of translation, when we are making a translation, right? So it tries to understand, okay, this was the input, how I need to process it. You freeze the
like
way, just like
like
in your
I
machine
love
learning model.
it's like I like Apple. It will be
Mm-hmm.
more maybe relevant because Apple
Ah,
can be a phone also. Apple can be a food also. Correct.
correct,
So
correct.
which scenario it is coming? How
Hmm.
using this multi-headed attention it identifies?
Yes, that is correct. This is what is making a difference in this particular scenario. So let's say you say I love pasta. You correctly mentioned I love Apple. Apple can be a food. Apple can be a phone. But if you mention I love iPhone, iPhone is closer to Apple, right?
Yes.
Because iPhone is something that is when it comes when it is you are training the model, you are making a embedding which is is of iPhone, which is of Apple, which are closer because Apple makes the iPhone. It is a company that this particular product belong to. And if you compare it with respect to I love pasta, it will be at a distance, right?
Okay.
Yeah,
Okay. This processing happens inside.
inside, yes. Just like lots of calculations that we discussed yesterday happen inside the neural network. Similarly, these all calculations, these are matrix multiplication dot products that happen inside the neural network.
So inside that we will go in detail that some point.
At this point of time,
No, no, maybe in upcoming classes somewhere.
uh, If you want, we can go. If the time permits, we can go. But currently, it is not part of our curriculum.
Okay.
Yeah.
Okay.
Okay. Okay. We had a really good discussion. I hope it was helpful for others as well. It helped you understand how things are flowing in here, right? Let's just also go through some of the statements that I have mentioned for the point of discussion. Majority of them have been already covered. So these attention mechanisms allow you to focus on different parts of the input sequence. That's what our positional encoding is also helping us in. It also process and interpret all the tokens at once. That's what my self attention is. It does not process one token at a time. The whole input sequence goes as an input, and the model understands based on the input that it has got, right? And that's why it helps us long range dependencies within my statement. Let's say a statement is 15 words long, right? So it helps us understand the relationship and everything, dependencies of one word on the other, how much one particular word is dependent on a given word. Let's say there is a noun, pronoun, some adverbs available. They are not much related to something, let's say, which is a action being taken, right? Adjective is much more closer to what my action is being taken in that particular statement, if that is the case, right? And multi-ended attention allows the model to focus on different aspect or relationship between the tokens, right? That's what we discussed, that it helps us understand what the information is coming in my input statement through different, let's say, if I can put it, try to understand through different heads whatever the input has come in, right? And this normalization and everything happens so that model can we can keep the information that is coming in and process it on the same scale. If we do a matrix multiplication, sometimes the value can go higher, right? But without losing the essence, we want to normalize those values. That's where the normalizing of this vector helps us. And softmax is the activation function. So let's say you have softmax is a very good when it comes to averaging, not averaging out, but let's say you have something vector 0.1, 0.5, 3.9, 1.5, 3.4. Let's say this was your output that your model has given, right? So in this particular scenario, your this particular term has the highest impact on your overall output, right? This is 3.9. Rest of them are, let's say, 1.5, 3.4. 3.9 has the maximum. So let's say this will go much closer to, this will have a very high probability in this particular sequence. This will have the second highest probability in the overall sequence, right? So it reduces the whole vector that has come in the output between 0 to 1. Whatever the number of nodes that you have in your output, it reduces it to the range so that you can actually interpret what is the impact of this particular single node on your overall output. What is the probability? If in case you have, there is also something called temperature. Temperature we will discuss later on in detail, but this is where temperature comes in, where by default, let's say if you keep a temperature as 0, it is similar to entropy that we have studied in our schools. But let's say if you keep the temperature as 0, it will by default take whatever my value has the highest impact on my overall. In this overall scenario, whichever has the highest value, it will give the highest importance to that, and based on that, it will come up with some probability, right? But let's say if you keep a temperature which is higher, so that means your maximum value do not have the highest impact on your output. Maybe it will take some other value. So there is some mathematical calculation, there is some formula of this as well. If you want, we can go through formula, but overall, you just understand that this softmax function helps us scale the output, whatever the output that you have got between probabilities, that is between 0 and 1, and what is the importance of each of these element in this particular vector on my output. These are individual node that has come out, right? So that is my one of my activation function that is used in my neural network as well as in this particular scenario, right? So for now, we have discussed, we won't be going too much in detail, but I think we have discussed pretty good, I would say, to get a good overview of how transformer models are working internally, right? And This
So
can help
see,
us build it further.
yeah.
Yeah.
See, like you said, temperature is depends on the soft max. Maybe the temperature, I think, is the parameter. Do you explain that parameters right in when you come to prompt and all?
Yes. So temperature is something, let's say you are getting this in the output. Let's say your output layer has, let's say, 10 nodes or 10 neuron, right? So
Mm.
every time whatever the process has come, you will get something which is of 10, 10 each node will have something in output, right?
Yes.
But which node should represent what? How will you know? Let's say you have something in your neural network and something has come up in here, right? Each node is coming up with some number which is like this 0 0.1, 0 0.9, 3, 0 0.5, 3.5, 9, 1.5, 3.5. Like this, you have 10 different values, right? So
Mm.
how much this 3.9 has impact on this overall? Or if you say, what is the share, not directly share like you do 3.9 divided by sum of overall this, it is not that. So the internally the formula that is e to the power xn upon e to the power xn summation. This is the internal formula. When you add a temperature, it can go by T. This is the temperature. This is the mathematical formula that goes inside. But overall, it is all about how much importance your individual value has on the overall output that you have got. If you set a temperature which is very high, your biggest value may not have the highest impact on your output because your temperature is reducing that impact.
When you keep the temperature, the this will become more maybe creative. Output
Yes,
goes more
yes,
creative.
exactly. That's when I was refraining from using those word creativity, randomness, because that will come later on when we are going to discuss. But it is the same temperature,
So
which we are reducing the temperature. That means we are reducing the randomness, and only the maximum probabilities will have the highest impact on my output.
yeah, so you when you are taking most probable means that will be very the maybe more
Likely,
no,
yes,
no. For example, this will be the more apt word you are picking up when you are putting temperature high. It may take as that secondary words. That means it create an or maybe a different, maybe
correct.
more this thing. It will
Hmm.
go right.
Yes,
Well,
it
like
does
that,
not pick
all other
the,
parameters. There are so many other parameters we set for an LLM, right?
yeah.
When you do that, so how it is impacted in back in settings, like you explain in softmax is
Mm-hmm.
or is the where this temperature will play.
Uh-huh.
Okay, like that
Mm-hmm.
other parameter also we will have some details that okay this maybe we are they will be tweaking it using this area of the encoder or decoder.
Yeah, so in when you are using the LLM, you do not have too much of control what is happening inside. You do
Uh,
not have
but
the control
but
on which activation function
but
do you are
these
using.
parameters how they tweak it or how they where they use that maybe to tweak it because here when you do make it you may be taking the second and third based on the temperature,
Yeah.
so you may be taking the second probable third probable like that we will take right. You know?
Yes.
so
Yes.
so like that we will be able to understand other parameters also.
What are some of the other parameters you are referring to here?
In LLM we will have other parameters na?
Like,
Like temperature maybe like
temperature is one. What are other parameters you want to mention here?
1 second. I have to check.
Sure. Is there any other someone wants to ask anything? We can proceed to the next topic. Or if you already understand, maybe you can put that. If you have any doubts, please speak up. Now is the time. Okay. So nobody is asking. I will assume that it is clear. And definitely you can go back and deep dive into this transformer. There is this
Top k
transformer.
there is parameters na top k all that parameters are there na I
That
think.
is something else. Ashok. Top K is something else. Top K is not related to what you are using here.
Okay, when we define parameters, I think this LLMs,
Uh-huh.
we give this kind of input also along with the right.
Yes. Don't
So
worry,
that
we'll come up there. Don't
okay,
this the
okay,
top
okay,
K temperature, everything we'll discuss when we are there.
okay,
Right now, this top K is nowhere related to what we are discussing at the moment.
okay.
Yeah. Okay. Are you guys there? Anybody else? Only me and Asoka discussing.
Yes, we are with you.
Okay. Great. Thanks, Kalpana. Um, okay, maybe in the chat you can put who all are there. Maybe put Y in the chat if you guys are active. This information might be overwhelming for some of us, but trust me, I have tried the easiest possible so that you can grab a broader overview of how things are working internally. Okay, thank you for the responses, guys. Okay, so since we have some brief understanding of the transformer models, these transformer models are then evolved further uh, to build the use cases or the Gen AI or the large language model that we have out there in the market today, right? But before we move into the large language model, let's spend 2 minutes to discuss what is AI and what is generative AI. What makes the AI generative, right? Maybe if someone uh, wants to share their views, the difference in AI and generative AI. No? Come on, yaar, AI and generative AI. There is a lot of buzz for like a couple of years around generative AI. Everybody wants to uh, learn generative
See,
AI, use generative AI. Yeah.
AI is a complete, it's a complete space, and Gen AI is a subset of deep learning, and deep learning
Gen
is a subset of machine learning. So all these,
Okay.
the combined is a AI. Basically, if we bifurcate the AI, it's a machine learning where it is the
Mm-hmm.
less data, less amount of data you can predict, create a model which can predict, which provide you predictions from that.
Mm-hmm.
But in the deep
Okay.
learning case, you require a huge amount of data for creating any kind of a model
Mm-hmm.
for prediction. But in the
Okay.
generative AI, it's like it's learn and regenerate for new tasks,
Uh-huh.
and learning from the previous task by using pre-trained models.
Okay.
Exactly.
Okay. So yeah, you mentioned right that uh, we need training, but one difference that I would mention in here is for generative AI also we need lots of data for training. For AI also we need data for training. For generative AI also we need, and for generative AI we need even huge amount of data for training, right? But yes, they all are different. The small input can help us generate the output, which is much higher than what we would have got in the conventional scenarios. Any other point someone wants to highlight in here?
So conventional AI is just like what we discussed yesterday. Like it learns the patterns in it and tries to predict like kind of like, let's say, if classification is or no, those kind of. But generative AI, it generates the text that is like, if you say in the text, it
Mm-hmm.
generate by learning, it generates some new context,
Mm-hmm.
or like if in terms of text it learns, I mean it creates new text.
Mm-hmm. Yeah,
So
that's correct.
It's actually a part of NLP. Is basically generative AI is a next word prediction altogether. If you look at in a high
Mm-hmm.
level, it's a
Yeah.
next word prediction where other maybe classic AI is it's it can be a numeric prediction or it can be a maybe specific to that data set. It is that way it is customized. Okay,
Yeah.
to the particular data set. Here it is generic text prediction.
Mm-hmm.
All that happening is on that only. Next
Yeah.
word prediction. That's
Yes. So yeah, that is correct. We are just predicting the next word, but in terms in here, it is not word, it is a token. A token can be a
Yeah,
word, a token
maybe.
cannot be a
Yeah,
word. Yeah,
ideally, it's an embedding. We need to get that is
correct.
token. Yeah.
Yes, that is correct. It is, we are just predicting something which may or may not be there in my training set. It will predict something that you wants to generate out of it. In my conventional AI model, it's very sophisticated, very restricted uh, in terms of what we can do in there. Let's say a good example of AI, it can be, let's say, self-driving cars, right? You understand in what scenario what to do. If there is something coming on my left, okay, I need to move a little right so that I can be away from that, right? And let's say if there is something on my right also, okay, then in that particular scenario, I might need to slow down. So these are some of the observation that are feeding that get feed inside my model, and there is some response that is generated, some actionable response that is generated. But in terms of generative AI, we are generating something, we are predicting something which does not even exist. We are being creative around that. If you have seen, you just ask, write me 1,000 word essay with a small input, you can have 1,000 pages of 1,000 words of essay that is generated, right? So it is all about generating with the help of AI. That's what make it little different, or I won't say little different, a big different from my artificial intelligence. Artificial intelligence, you are giving different scenarios on which the model responds and take action. In generative AI, it you do not even give those scenario prior to what when the model needs to take all those decisions and take actions and everything, right? So this is a brief on what is the difference between AI and generative AI, how they differ, and why generative AI is in so much of buzz, right? One of the use cases, let's say, can be let's say creative writing, right? Let's say image generation, image, or let's say video. You just tell what needs to be done, and it based on the training, whatever the training the model has got, it tries to get to as close as possible to answer your question. One can be, let's say, in enterprise level. That's what I am primarily working on, is to convert text to SQL. SQL, anybody can write SQL. Who knows SQL, who understands the data, they can write a SQL, right? But this is not a scalable. With generative AI, all these processes are getting a lot scalable, faster, much better, which reducing the human dependency, reducing the chances of error sometimes. But that needs to be controlled, because the model is trained to predict the next token. Whether it is a correct token or an incorrect token, that remains to be a big point of discussion. But it is just trained to predict the next token. When you are doing a creative writing, it is just predicting the next token. Maybe you are asking it to write an advertisement or a poem or something. It is all about how you ask the model. That's what we are going to discuss in today's discussion as well. How you ask the model to do something, how you can improve on what you are asking, so that model understands it better, right? That is something called prompt that we are going to discuss next, right? So this is what makes the generative AI so different, and that's the reason the generative AI is in so much of so in hype for last couple of years, because it can generate the stuff that does not even exist at the moment, right? Which can be consumed, which can have a number of applications. If anybody wants to add in here or have any doubt, we can take it up, and then we will be proceeding further for next discussion.
Yeah, so generative AI is a subset of AI where we can generate text, images, right, and videos, and where AI is like artificial intelligence, it means self-driving, right?
Mm-hmm.
We have like human is working, but no, machine is
Mm-hmm.
working like a human. And the example of robot is also the example of AI, right? Because we are
Yes.
here, we are not generating the content or anything.
Mm-hmm.
We are operation like a human. That is why it is
Yes.
artificial intelligence.
Mm-hmm.
But generative Gen plus AI. That means we are using the brain, but rather than just taking a decision, we are generating the text based upon the prompt. Whether you
Yes.
are asking for the text, whether you are asking for the video, whether you are asking for the images, or whether you are asking for any of the summaries, it depending on the text actually. That means
Mhm.
it generates the text using the brain, which is artificial brain, right? Not a
Correct.
human brain, right? So
Mhm.
this is the whole difference between them, right?
Yeah,
With the
correct.
example.
Correct. That's correct. Yeah. Anybody wants to add in here? If you have any doubt, or shall we proceed?
When you train when you ask for example, please give me this program or this query.
Mm-hmm.
So it's okay. It's a next word prediction agree.
Mm-hmm.
So how it will give that exact program? It will go to that
Mm-hmm.
exact program. Is there any extra activities happening in the backend which we may not be knowing, but we are giving that text
No,
and
we are not giving anything extra. You are just giving that one statement
no,
and
no.
it
I
is
just give me a
generating.
program front end to create say so and so. Let's see login page. Just
Mm-hmm.
I am writing only the login page. Give me a
Mm-hmm.
program.
Okay.
So when it is trained, so it may not trained program also for creating a friend login. Okay,
Mm-hmm.
but
Mm-hmm.
we to get connected that okay, I have to give this. I have to give this when I ask this question. I have to give this output predicted.
Yep. Yep. So,
So it may not
okay.
be that way. It may not have trained right in the
Yeah,
beginning.
correct. So, maybe the model was trained on how the login page looks like. Maybe it was not trained. Okay, let's say it was trained on writing, let's say, JavaScript or TypeScript kind of code, or let's say a Python code. It was trained on those key, okay, how to write a code. It was
Mm.
trained on how the login pages looks like, right? But when you combine these two, okay, this is how I know how to write a code, and this is how a login page looks like. Okay, let's try and generate a new code using my understanding of the code and using my understanding of how the page will look like. Let's now generate a code. You must have seen there are some model which are good at certain tasks. Like
Mm.
you have DALI, you have
Yeah,
like Whisper, right?
mm,
Which are particularly which has expertise on certain tasks. There is a model called Cloud
mm,
by Anthropic. It is particularly trained to generate code, right?
mm.
There are other models, Mid Journey and all that were in quite hype, which are particularly trained to generate images,
Yes. Mm.
right? So it is based on what the training has been happening. There is something called pre-training,
Mm, mm, mm,
and then there is something called inferencing.
mm,
Please bear with my handwriting. So pre-training is what? You are training you are exposing different scenarios, all the possible scenarios to your model. It is like you are making the model to walk first, initial steps. Okay, you make model to understand, okay, what is the, how to get to a next token, how to get to a correct token. That is something that we will talk later. But
mm,
how to first predict a token? That is the
mm,
first case, right? How to
mm,
come, let's say when a user is asking for function, that
mm,
function has to come up. That is something that will come later. But initially, you just understand how to predict the next token. Once you understand how to predict the next token, then you give additional context. You give the feedback. Okay, whatever you have generated was correct or not correct. That is called RLHF. When what we discussed yesterday, that human is passing on that feedback, that whatever the output was generated, whatever the token was generated, was it a correct token or not a correct token, right? So based on that feedback, it adjusts and then moves in the loop till the time it is hitting accuracy that whatever has been asked is being provided or it's being generated by the model. So in pre-training, the model is just trained to learn those basic steps to
So we
generate
will
some of the
learn all these
output.
steps.
Sorry?
We will come to that steps of
Okay, so
LLM.
this pre-training, this fine tuning is something that yes, we'll be looking into. But
Mm.
this pre-training is something that companies has been investing millions and billions of dollars, not in terms
No,
of
I'm saying as a
training.
concept at least we can go through that.
Yeah, that's what we're discussing right now. No? In pre-training, you are exposing your model with the data so that it is able to predict the next token. It can be image data, video data, text data, web script data. It can be PDF, audio. It can be any data
So
that
the
you are
model
exposing your
weight
model
will
to,
change according post
according to
pre-training.
whatever you are training initially. And
No,
then when
no,
you are,
there will be initial LLM model, but when I do the pre-training, the again the weights will be adjusted according to the pre-training.
there is, yes, whatever you are training. Okay, so for all the training that we are doing, what actually we are doing, we are adjusting those weights only.
Okay.
Internally, the model weights are there. We are doing that only.
So,
Pre-training, we
see,
are adjusting the weights in general to predict the next token. In
mhm.
fine-tuning, we are adjusting the weights to get a specific output. That's what we are doing in fine-tuning, and then we freeze those weights. We do not change those weights, and that's when we come to the inferencing stage of the model, where we are using just the input and getting the output. Internally, we are not changing anything. All
Inferencing,
the
can you
model,
explain inferencing?
yes, we'll come to that. We have not even
Eh,
started inferencing yet.
Okay, okay, okay. Yeah, that's why I'm asking. These terms you will come again, right? Maybe with some.
Yeah, we are discussing right now.
No, no, inferencing. You are saying that it will come later stage. That's
Yes,
why.
all the use cases that we are building, all the application you are using right now, they are all inferencing. You are doing inferencing. How you are doing that inferencing, that can differ, but how you're consuming the information that is generated by model is all inferencing. You are giving something in the output and you are generating some output in that case. That is what inferencing is. You are not training the model, you are not fine-tuning the model, you are not working on updating or modifying the weights, modifying internals of the model. You are giving an input and getting the output. That's what my inferencing stage of the model is, right? So there is something called pre-training. There is something called fine-tuning. In fine-tuning, I'm modifying some of the weights of my model so that model is able to predict the correct token in the given context, right? So fine-tuning can be of two types. First of all, the model was trained to predict the correct token when it was initially trained, right after my pre-training. That is one. Second one is once you have the model ready for inferencing, you want to again update some of the weights. That is what fine-tuning that many of the use cases are around. Let's say in our scenario, when we are building text to SQL, we are fine-tuning the model. That means we are changing the weights of some of the layers of my large language model so that it can adjust according to my use case. I'm exposing the input and output data, properly labeled input and output data, clean data. So because the model is going to learn from this scenario, right? So there is a huge amount of time, huge investment that goes into fine tuning as well. And majority of the effort goes in preparing the data subset, which will be used to fine tune this model. In pre-training, you can just expose to whatever data that you want to, so that the model is able to predict the next token. But when you are doing a fine tuning, you need a specific data, formatted data, input and output, labeled data, and everything, because that's where the model will learn about the accuracy, how to predict the correct token. Correct is the key term in here.
So here these LLMs are actually unsupervised. Certain level, it is a text data. Okay,
Mm-hmm.
it's a text
Mm-hmm.
input which is getting trained from in the internet. Okay, whatever is
Mm-hmm.
available in the internet. So how we get that trained? For example, next word prediction. So
Mm-hmm.
how we, because there is no label such things in text data, right? Correct.
Initially, for pre-training, if there is no labeled data, that is okay. But when we are doing the later
But
training,
the
there we need
training
it.
need, see, training need the weight adjustment. So the weight
Yeah.
adjustment will need somewhere we need to tally that okay my cost is matching. Okay, my zero error is zero, or I am predicting whatever is
Okay.
the right thing which is need to be predicted. Then accordingly the weight forward and backward propagation will happen according to that, right? So we
Yep.
need something reference point for making any training, correct?
Okay.
Whatever is the way we say. So how
Mm-hmm.
we tweak the text data which we maybe scrap from the internet, okay, to work as a training data.
Okay. Okay, I'll repeat myself. I think we have discussed this just a little before, that in initial training, we do not need a label data. But when we are moving towards predicting the correct token, we
So
need that
that's
labeled
a
data.
how the, without labeling how it will train.
You need to label it. Who said that's what I mentioned, no? That you need that
Okay,
effort, you need that
the data
resources to
it may
label
not
data.
have label, but we have to make some labeling process need to be done.
Yes, that labeling has to be done for that model to understand what is correct and what is not correct. And whenever it is predicting, I mentioned that RLHF, reinforcement learning with human feedback. That human feedback also goes in. We are also telling the model, okay, this is what you predicted and this is the correct that should have been predicted.
Yeah, that is
And
one way,
then,
but that is very costly affair, right? Because somebody is
yes, it
sitting
is.
and saying yes or no.
Yes, it is.
It's for entire world questions. Okay,
That's why large
that
language models are not easy to build.
somebody is sitting and saying that okay, what you predicted is correct or not.
Yes,
But
correct.
that you can do for fine tuning, but I don't know whether you can use it for initial training.
Initial training, you do not need label data. I mentioned, no.
So how it will
In
be done? See, for example, it's my read on the internet.
Mhm.
I read somewhere it is like that. What we do is that we skip some words
Mhm.
from the text we fetch from the internet, and they have to like a fill in the blanks. So the model try to fill that blank. So if we fill it with the right word, okay, it's good. Otherwise, it will be asked to again adjust the weight.
Don't you think that is again someone passing on the feedback
No, for example,
for missing word?
this is an app. See, this is an apple. So apple they remove. Okay, or this is not that may not be a right
So
example.
someone is removing that word, right? And then
Yeah,
exposing the word again.
at random we can remove that automation we can do.
Even
That
in
much.
random, but it is being removed, right?
It is processed. We pre-process the data with some labeling. We will pre-process. Okay, but
In
that is very easy because that no-brainer job. We can just randomly pick up the words and remove it, and then we can ask the model to predict that. And if it is matching, that can be automated. But somebody sitting and answering, checking the answer, reading their answer, and seeing whether it is correct or not, or it is this much accurate. So that kind of feedback is very costly.
yes. So both the stages are there when it comes to the model training. Initial stage is what you have read over the internet that yes, we randomly remove certain word from my statement and then ask model to predict and then give the feedback. That is also a feedback mechanism that is there and that is also automated, but that is also human feedback that is going in. Whatever it is predicting, whether it was correct or not correct, that is a feedback that was generated,
So
right?
is that the way initially the model get trained? The
Yes,
bare metal, the initial first step of the training will happen like that, right?
correct.
Okay, then so that stages only I was asking. So what is the stage by stage if you look at? So this is
Mhm.
the first stage. This will happen, and the second stage maybe further improvement. Then third stage further improvement like that maybe. Then customization or whatever it is happening.
Okay. So I believe that's what I mentioned that in the first stage we are exposing the data which is not even labeled, and then second stage we are exposing the data which is labeled. That labeled can be a human labeled input and output. That label can be a randomly generated process by human, right? That goes as a
So
feedback
not
and then
label that again
goes in the loop.
that's a gap for me. The not label how it will be tuned.
Okay, so let's say you have a statement which has 10 characters,
Mm,
right? And randomly you remove one word out of this statement and then
mm.
you hide this word from the statement and expose the model and ask whether
That is
what is that
that
word.
we say that automated labeling. That's what we discuss, right?
But that is labeling.
Okay, that is labeling, correct.
That is automated, but that is labeling.
Okay, so the no that is but no label. Initially, you mentioned that no label. You meaning that this is the one that no
No,
label
no
means
label is something that you expose the direct statement and the model is learning what is the next token based on whatever the input that you are providing. Then when it
okay.
has learned something, what comes the next to generate
Okay,
some
okay.
probabilities, generate some token that will come next. Then you expose how, or then you take it
Okay.
towards how to predict the correct one. This is
Okay, for
towards
example, one
how you
sentence,
go to the correct one.
last word, next word, you will not expose. Then, okay, it will predict for the next word. Okay, okay, understood. Okay, sequentially it will go.
Yes, right.
Okay.
And yeah, and I would also request whatever that we are discussing, maybe you guys can read something, can expose yourselves through some different articles that are out there, some videos that are out there that will help you build the understanding of how things are flowing. Not everything and anything we are going to discuss in the session. There can be n number of things which, if you go deep dive into it, we will come across. Um, but due to the restriction of time, we will be taking some of the things at broader level, but I'll make sure that everybody understands what is happening at a broader level internally. That's what my discussion was focused on yesterday and today, and it will be in further sessions as well, right? Do we have any doubts, any question we can take up next, and then we can proceed further. Are you guys there? Put a yes in the chat if you are there.
Yes, we are here.
Okay, do
It
you
would
think
be,
the discussion? Yeah.
yeah. It would be great if you can share some of the resources for us as a beginner.
Yeah, sure. I'll do that. Don't worry. I'll share. So there is one YouTube channel called Three Blue One Brown. That's really nice pictorial and animations and everything of how things are flowing internally. There's a series on neural networks. There you understand the transformers, the neural network, the large language model, how a token is processed, everything that is really good over there. So maybe if you want, you can uh, take it from there. Please type in the chat. Okay, I'll do that. Uh, so there is a series on neural networks. Maybe you can take up that. And if something goes bouncer, maybe you then before going into that, or maybe if you watch again and again, you will get understanding of what is happening, or maybe you can browse through other videos over the internet as well. But this is one that I would definitely recommend. No audio? Can you guys hear me?
Yes, I can.
Okay. Prachi
Channel
says
name
no
is
audio.
very different.
Yeah, but the learning is awesome. There is one from Andrew Karpathy. You can also uh, go through his YouTube channel. There are a couple of videos, but really awesome. Right? Okay, so let's move to the next agenda of discussion planned for today. So what is a large language model? Large itself suggests it has huge parameters inside, right? There are models with 70 billion parameters, 300 billion parameters. So the large comes from there that it has huge parameters internally that process the information and to generate whatever the output that it is generating at the moment. Language models are like they are processing the natural language into something whatever the model is particularly trained for. Let's say you have a text model, you have an image model, you have audio model, right? Audio model one is from OpenAI called Whisper. Video model is something from OpenAI. Image model, it's called DALI, right? Text model, we all know that GPT models 3.5, 4, 4.0, there are so many models out there. Mistral, Llama, right? So these are all the models. They are all text model, right? So there is something called open source and there is something called closed source. I'm sure you guys must have are aware of these terminologies because this is a key difference in the adoption of a model. Even in my organization, when we wanted to pick what particular model to go for, or when we are discussing it with the client has a huge concern over what kind of model that we are using, and that is again what is open source and what is closed source. Open source, as in the name itself suggests, the weights the parameters, the model itself is open source. You can download your model, run it in your local machine, which do not need internet, which do not need any, which do not have any dependency. So whatever the data, whatever the input that you are feeding into your model has a zero risk of leaking whatever the information that you are using, right? But in terms of closed source, whatever the information, the model is hosted somewhere else. You do not have any control on the model. You are just being as a client, you are just passing a request, something is processed and you get a return response to that. There are some risk in that scenario that what if whatever the information that I'm sending, the company, or let's say whatever the whoever is hosting the model, they are storing whatever the input that you are sending, and they can use this information to tune their model, right? When it comes to enterprises, information is very critical, and they do not want to share their internal information with like any model just like that, right? So that's how that's what the difference in open source and closed source. Open source are some of the model like Meta. There are a number of models on Hugging Face, right? Llama and all, Mistral. We have this recently the Chinese model that got famous, right? DeepSeek.
DeepSeek.
Yeah. So these are all the open source model that are out there in the market. You can download them and you can host in your local machine. It's just that you need that local resource hardware to run that model, because model is quite heavy. We just saw what amount of calculations happens in one single node or one single neuron. And when you expose it to billions of parameters, the calculation goes heavy and you need quite a heavy machine to do those calculations. For closed source, OpenAI is a good example of closed source model. The name has open, but they are not open. They are closed source. You just use their services. You send the request and you get the information back, right? So open source is you can host it yourself, and closed source is something you cannot have a control on. You cannot host that model. It is there. Um, in our organization, we are using open source as well as closed source model depending upon the client's requirement. We are using Llama 7B parameters, 70B parameters, as well as we are using OpenAI models. OpenAI models are just whatever they provide, we are hosting them. That's it. We are hosting it on Azure. So Azure provides that service as your OpenAI models, and we are you leveraging the potential there, right? And then there are differences on how you use the model, right? Initial days, there were labels that you need to provide that, okay, this is the instruction that you need to do. This is the input question, and then what is going to be the output for that particular scenario, right? So that these models were called instruct model, where you have three different labels, right? One was instruction. Okay, you need to do something, make sure you do this as well, also this. And then you have an input question, which was, let's say, if I give you example, in our exams, right, there was something called as instruction that was at the top, which was applicable on different scenarios. That was my instruction, right? And then you have question. You just take the question based on whatever the instruction are provided, you answer the question, right? So is if the model is tuned, and this depends upon how the model is tuned or the model is trained. If the model is trained in this kind of scenario, the model will perform better in these kind of scenario, because model expect there will be some instruction provided, some input, and it needs to generate some output, right? Versus there are something called chat model. Chat models are where there is a conversation going on. Something goes in the output, something goes at the output, right? And here instruction are part of the message that you are sending into the model, right? So you did not need to set a separate instruction tab before. You just set instruction tab once, that's it, and then you are moving for the conversation, natural conversation that you can expect from a language model that's happening. And then we have a reasoning model. Reasoning models are something when they are tuned to answer a question in a certain fashion, like the DeepSeek model. It has internally some instruction available when it was tuned, and based on that instruction, it is following whatever the instruction it has followed in its training. It is replicating the same instruction in my inferencing stage whenever I'm asking the question. So whenever you ask a question, it tries to answer it in from different scenario, try to reason why it is generating what it is generating, if the generated answer is something that was asked in the question, or it is something randomly coming up. So it gives that question mark on itself whether the output that is trying to generate is correct or not, and then it comes up to a conclusion answer. Yes, reasoning model can be time taking because it is processing lots of information internally, questioning itself in different scenarios, and then answering the question. So reasoning model can be time consuming, but they can be pretty accurate in some scenarios because it is already doing some questions on the output that is generated, right? So these are some of the types of model that are out there. The model size depends upon how many neurons it has internally. Uh, we have already discussed that. Any question till here? Then we'll be moving forward to some of the key terminologies that you're gonna come across uh, in our day-to-day use of any large language model. Any question in the discussion? Types of large language models.
No, it's good.
Okay. So first and the most important term in here that we can start with is the tokens. What is a token? Token, as we have already discussed, you can, if you broadly take it, token can be taken as a word, but not all words are token, right? Our token is the smallest unit a model can process at a one time. The smallest unit as it can process, that means whatever the input that you are sending in, you are sending as a statement. This statement is broken down into smaller pieces, which is then sent to your model. All token at once, but it is broken down into smaller pieces. Smaller pieces as in, you remember from the statement, it used to look up into a vocabulary dictionary or lookup table that it had, and from there it used to get the embeddings. So these are the smallest possible value that it can find in that lookup value, and it can produce that embedding around it. So that's my token. Whenever a model is generating something, it is always predicting the next token, because token is the smallest processing unit for a model, right? It generates one token at a time, right? And then keeps on generating based on whatever the input that you have asked till the time the target is achieved. So tokens is that tokenization is the process of converting that input statement or whatever the input is into tokens. And I have also captured the link for this so that we can go through that. Let me see if I can open that link and we will see how the tokenization look like. So this is OpenAI is like just for the learning purpose, how the statement can be broken down into tokens. What when I say one token, it is not necessarily always equal to one word, right? And let's take one sample statement. Let's take this statement only, right? Just taking a random statement, you can take any different statement as well, right? So can you see? These are the different tokens it has generated. Input for you, the input, if I see, I don't see any statement broken and any word to broken down here. Let's see some examples. So do you see these color coded? These color codes are something that the model is internally breaking. The model is tokenizing the input statement into one single token. One color is one token. So here many is one token. Space words is another token. Space map is another token, right? So these are different tokens that it is generating.
So,
Different
so
models can have.
yeah, you can click on token ID. Let's scroll down.
Sorry.
Token ID, yes. Is there anything? Yes, this is the token ID. Okay, sure.
Yes. So this is the token ID. Like this is so from the lookup table that we had earlier, right? That lookup table, each individual token has something to look for, right? It has some ID. This is the ID that has come up. So if this text is called up and it is used, it will be this ID that will be called to generate the embedding, and it will be taken further, right? So this is my tokenize. This process is called
This
tokenization.
this ID pre created IDs for that word.
Yes,
Many will have. It
yes.
will change
This
according to the position. No,
no.
this
So this
six.
is the original meaning. This is called static embedding. It does not change. It is a
So
lookup value
so how many
or reference.
maybe words are there like this? Maybe
There can
normally,
be like millions, depending upon how many words are there in your
each
vocabulary.
model will have different
Yes.
set of embedding.
GPT models, I think there are 50,000. I'm
50.
not sure, but maybe you can confirm, or maybe I can look up and get back to you
It
on
will
this.
be like a full dictionary of
Yes,
English.
correct. And this is the ID. Each ID will have a vector, will have a embedding available for each of the token.
Hmm.
So this is the key, or this is the ID of that vector that is there.
So every time this word, one word will have the same ID, right?
Yes,
It won't change.
yes, it won't change. One token will have the same ID. Okay. Let's move to the next thing. What is my context window? Context window is the uh, maximum information the model can process. Token is the smallest information the model can process. Context window is the maximum input that you can provide at one time to the model. Uh, if I can show you context window of some of the models, open. Okay, so I'm just browsing through, right? And let's see what is my context window of, let's say, 4.1. Do you see this? This is the context window. That means these many tokens you can give in the input at one time, right? There is always a limit how much a model can process depending upon what is the number of neurons in my input layer. This is what decides what will go in your input. And this is a fixed length for a given model because when a
So
model
almost
is freezed,
1 million is there, right?
yes, it has 1
Yeah.
million. The earlier model used to have a context window of
But it
32K.
may not be open for everybody, right? Or is it open for everybody?
That
Or paid
depends.
version?
That depends. It is a closed source model, so completely and everything is controlled by OpenAI.
Okay.
If you are doing a open source model, you are hosting itself, you can control
So
everything and
output is
anything.
32,000 only.
Output is 32,000 tokens that it can generate at one time. If we see some different models, let's say, let's take some
Also,
older model.
this 32,000 is sequential production or it is sequential only, no? It can be produced sequentially only.
Yes, model always produce sequentially only.
That is a one disadvantage actually, right? It will take time.
Yes, it take times, but that's the process. मतलब, um, to even model to produce output, you will be channeling it through one single layer, right? That layer itself can have multiple nodes, but to interpret it, you will interpret one token at a time, right? So that's what this is. So this is the context window of this model, which is uh, how many? 2 lakh. 200,000. This is the context window of O4 mini, and it has the output token length of 100K, that is 1 lakh, right? So different models can have different context window. So now you understand what is token. Token is the minimum smallest unit a model can process. Context window is the maximum input that the model can process,
This
right?
knowledge cutoff, it won't change later, right? It will come as a new version if it is
Okay.
this
Yes, so
knowledge
knowledge
cutoff, right?
cutoff, yeah, knowledge cutoff is like you are using some data to train the model, right? You are collecting the data from internet. You are collecting the data from some open source knowledge that is available, some library or something, right? And till what date you have the model has the knowledge of. So this particular model has a knowledge till June 1st, 2024. Any information after that was not included or now was not displayed to the model. And this is one of the disadvantages, and that will come up later of large language model. That whenever you are asking something that is happening in real time, the model directly cannot answer those questions, and it needs something which can get that additional information, or you need to
It
provide
won't
that
change,
additional
right?
info.
In 0 for mini in the life cycle, it won't change further, right?
If they update this
But
model,
it
it
will
will
be they'll
change.
put some other version number, I think. I don't know.
Yes, yes, there will be some other version number for that. So it's like some unique identifier of a given model at a given date that
Yeah,
is
this
there.
reasoning token and thinking, sometimes it is showing thinking, reasoning.
Yes. So again,
What
that's
is
what
the
we
difference
discussed.
between the normal and the other one? Yeah.
Okay, that's what we have discussed just a little before. That reasoning model has itself internally configured. It can raise some of the question internally before giving you the output, right? So you can enable that configuration as well. Earlier model didn't have this. If I go, let's say 4.0, 4.0 do not have this support, right? 4.0 is a model that was that has a cutoff date of 2023. It is even 1 year older model. As soon as the model are evolving over time, they are adding some of the advanced functionality in the model training itself. Is reasoning same as chain of thought? In a way, yes, because you are making the model to think through a certain process before answering, right? And that's what we do in my chain of thought prompting, that we are making the model to follow a certain pattern. Some of the things that initially were not part of, like the parser that we are going to discuss. Initial model didn't have the parser. They didn't have the capability to follow a parsing technique. But later on, as the models are coming, they are compatible with the parsers. That means when they are trained, they are given those instructions, they are given, or they are exposed to these kind of information, and they are sticking to that when we are inferencing the models, right? We'll discuss parser right in a couple of minutes. Embedding is something that we have discussed. It is converting a textual data or a image data or any information that is available before feeding into the model, because model do not understand language. Model do not understand model only understand numbers, numericals, information, right? So converting that input information to numbers, that is called embedding. This process is called embedding, right? And there are different techniques to convert that. There are different models to convert that embedding, right? And then there is something called semantic search and cosine similarity, right? Semantic search is something, let's say, if I have a embedding for a word called Apple and we have a embedding for a word called iPhone, right? Do you think these words are similar in some way, right? Apple is a company which makes iPhone. Their similarity would be much closer compared to Apple and let's say a car, right? Because Apple do not make a car. The difference between these two vectors would be much. And this semantic search happens based on the cosine similarity when we come to the large language model or natural language processing. And what cosine similarity is, you take, let's say, if I can write it. Yeah. So let's say you have one vector, let's say I'm trying to represent in 2D space, but it is much more dimensional. But for simplicity, let's take it in one way. Let's say this was vector for Apple, that's right? Let's say this was Apple, this was a vector for car. And let's say this was a vector for iPhone, right? So cosine similarity is the angular distance between these vectors. And when I say angular distance, that means this distance, this distance. This is called my cosine similarity. The magnitude can be different. Irrespective of the magnitude, we are just referring to what is the angular difference between the two vectors, and whichever vector is closer to my or let's say they have a lesser angular distance, they are much closer. So in this particular scenario, Apple and iPhone are much closer compared to Apple and car, right? And similarly, iPhone and car, they are all gadgets, they are all machines, right? They are closer compared to Apple and sorry, iPhone and car and iPhone and Apple, right?
So
So
what will be
that's
maybe the length will determine. Okay, angle will be the similarity.
Mhm.
Then the length of the vector For example, it's a zero, maybe very closer similarity, but the
Uh-huh.
length is to difference is there. So what will be the can be the reason for that?
No, so the length of your vector can be anything, irrespective of that magnitude. The magnitude of your vector decides what will be the length of your vector. So irrespective of that magnitude, we are bothered about in my n-dimensional space, in this particular scenario, in my
It depends
two-dimensional
on the
space.
it depends on the size of the word or something like that. It will be different.
It can depend. It can also depend upon what information it is holding,
Okay.
right? So irrespective of, because we are bothered about how different or how close they are, right? If there are other methods of calculating the distance between two vectors, Manhattan distance, dot product, Euclidean distance, but these all of the different methods, they are not considering the angular distance. They are
So
considering,
how
okay,
we
they will go
make
one
this
by one.
vector? How we make this vector? For example, the word maybe India and Delhi will come closer, right? Because it's the
Yes,
capital of India. Okay.
yes.
So initially, how we make the position of this vector based on what methodology we will make that positioning?
No, so this positioning and everything, this is for understanding. Internally, this is the n-dimensional space, and humans do not have the capability to go in that dimension. OpenAI 1536 is the dimension of that particular vector. We can go into three dimensions. Sometimes we can go into fourth
To
dimension, but
take two dimension, see,
mm,
there can be multiple dimension based on the maybe the this one
yes,
this is like a cap, is it a place, is it a thing, is it a noun,
okay,
pronoun, like that,
yes,
it will have multiple dimensions. Okay.
yes,
So I'm seeing that initially how we encode that to a vector. For example, I
yes.
have a word India, I have a word Delhi.
Let's say this is your vector for India,
India, yeah.
right? And this is your
Delhi.
vector for Delhi,
Yeah. Then
right?
there will be capital
There
also
will
one
be
word.
some difference. This
Yeah.
difference is called capital in this scenario, right?
Mm.
So if I this difference, if I add this difference to my vector India, I
Mm.
will get a embedding, or I will get a vector for Delhi. Let's say if I add it same, let's say if I'll get the place for my New Delhi, because New Delhi is the capital of Delhi again, right? Similarly, if you give Germany let's say might be lying somewhere in different
Yeah. And
different
my question is that how we decide the position, initial position. India should be placed at this
you
place. When I get a
have
word
a
India,
lookup.
where to be placed India, where to be placed Delhi, where to place
You have a
capital.
lookup, no? You have a lookup static embedding available for each and every word in the vocabulary. That
See,
embedding
we will
decides
have a
where this
see.
will lie.
We will embedded. See, we are embedding based on say 2 lakh total words are there. So 2 lakh this will be embedding number will be created.
Yes.
But where to the second dimension of that will be the position. It will decide the position, right?
No, the whole vector
The other
decides what the
dimensions.
position.
One dimension is the number. Okay.
Hmm.
Second dimension will be where to place it. The other dimensions.
No, it is not
How
like
do we
that.
relate? How do we relate? Maybe,
How do you plot a graph?
yeah.
Let's say you have
I just want to
one
know
comma two.
India how we plot. Yeah.
So it is like, let's say you have 1 comma 2. You go on a
No, that I
plot.
understood. How do we get the one and two?
This is a static embedding that we have. For each word in your vocabulary, there is a static embedding that is there.
Static. That's even static embedding. See, if we are direct converting the number to say 10001 to India, that I can understand. But when you make the position, there will be another dimension two will is coming. Correct. So that how do we that make that okay, it should come here. Initially I should say okay, this should come in this quarter or this position it should come. How do we that embedding, how it will happen? The meaning is lies in that embedding.
I'm not sure if I am understanding your question correct, and we are already hitting on the time. And but for now, what I would conclude this particular scenario on is there is already a static lookup embedding available for each and every model that is there, right? And
Ah,
it lookups into this. This
how,
float
how
is
initially
generated
that is
using
made
this
is a
only.
question. Okay, we can. It's okay. Not explain
Let's
today.
say it is for your understanding. You plate, let's say for India, you create 1001.
Hmm.
For let's say Delhi, you create 0110. This is for your understanding. Nobody else can understand it. Only you are understanding it, and that's what you have kept in this lookup information. You understand what this information is. Make sense?
No, no. Initial lookup table. See, initial lookup table also it should come closer, right? See, I can keep India in the first and Delhi in the last. So when I pull out the vector, it won't come closer. If I do random coding,
No,
coding.
based on
So
your
I should be somewhere. I
terminologies, it
am
will come.
getting that relation in my static table.
So whatever you are encoding it, you will be following some pattern, right? You are not putting
That's what
anything in random. If you are
that's what
putting
I
in
was.
random, it won't come closer. But
Yeah,
whatever the
yeah, yeah.
pattern you are following throughout your lookup table,
How
they
that
will come
pattern
closer.
is made, some idea we can get. That's only the question.
Okay, so whatever the logic that you are trying to put, let's say for the word A, you want to put something that whenever a word A will come, I'll add one to my vector. Whenever a word B will come, I will put 0.1 to my vector. You are putting in some logic, right? This logic is applied to all the word in your vocabulary, and that's how you generate it. And maybe we are taking everybody's time and we are already closing the time. I'll take a halt here. I'll add these rest of the topic in our next discussion, and we can start our discussion from here in our next session. Okay.
Ankit, yeah,
Yeah.
the PPT which you are showing will be accessible in study
Yes,
material.
I'll be sharing it. uh, I'll be sharing this presentation. I think this was my last slide for the day. But it's okay. I have three, four, and these are some of the importance. These terminologies are all important in our future use cases, right? When you talk about
Okay.
rate limit, temperature, hallucination, these prompts, and I also had prepared some hands-on notebooks for today's session, but due to time, we cannot go into that. But it was a good discussion. I hope everybody understood with the discussion that we were having today, and you are having some understanding, or I would say a good understanding of the base that we were trying to build, and now we'll be proceeding on the use cases, the whole agenda of the curriculum. Okay.
Yeah.
Yeah, please, if you have any doubts, we can close. Otherwise, if you have any doubts, please speak up or put it in the chat. Okay, I'll take the silence as we have understanding of what our discussion today, and we do not have any doubts. I'll be sharing the presentations and some links if I come across of the articles or the resources that you can go through, and we'll call it a day. Okay.
Okay. Thanks, Ankit.
Yeah. Thanks, Samshay.
Thank you.
Yeah. Thank you. Thanks, Vishnu. Thanks, everyone. Have a good one. Bye bye.